All right, folks, let's get started. So, a couple of announcements. Homework 4 is due next Tuesday on April 9th. And you got to keep track of how many late days each of you has had so far. And so you have the buffer of 7, so you got to keep that in account. And the project milestone is due next Friday on April 12th, and the homework buffer late days don't apply to that. So. So the outline for today's lecture is, for the first part of the lecture will be from me on summarizing the course and going over the strengths and weaknesses of all the topics that we have seen so far. And time permitting, give a quick primer on semi-supervised learning. And the second half of the class is a guest lecture from Ilya Sutskever. That's going to start at 6:45. And we'll have the break at around 6:30. So the beginning of the class, beginning of the whole course, we started off with this motivation from Jeff Hinton, where we saw that the like his argument that the brain has 10 to the power 14 synapses, and but the amount of data we process is not as much as the number of connections potentially in the neural network that forms the brain. So we have a lot more parameters in the data, and so that's why he motivates unsupervised learning, because you want to learn, you want to give as much data as possible to the kind of capacity that your neural networks allow you to do. And if you actually make these take these numbers into context in terms of what we're doing right now, we're hardly scratching the surface of these limits. For instance, the largest models that are currently being trained are the billion parameter language models, things like OpenAI GPT-2 and so on, and they're still not there in terms of 100, like 10 to the power 14 is 100 times a billion, so 100 times a trillion. So you can actually see that we're still yet to train larger models, and that the only thing that limits us from doing that is the kind of compute we have right now. And also the kind of data we are training on is still very small data sets. Like people consider ImageNet as still big right now, but not sure if you've all seen that recent result that ImageNet can now be trained to 75% accuracy in like 70 seconds. So we are definitely going to be training on larger models, larger data sets, and that was our motivation to cover this whole set of topics. So in terms of the specific topics that we've seen, we've looked at a whole bunch of models, different classes, autoregressive, flows, latent variable models, and then implicit models or GANs. And then we also covered what it means to learn representations without really having to generate the appropriate data distributions. So let's actually go over them one by one, like a whirlwind view of how the progress has been in each of these topics, what the pros and cons are, and what you can do as future work, and so on. So first, autoregressive models. On the left are samples from MADE, which you implemented in the first assignment, and they're just simple MNIST digits, and it's looking good, but still it's not really getting all the some of the 7s, like some of the 3s are not really good, and there are some digits which are just not clearly present at all. And just a year later, the Pixel RNN CNN model came from DeepMind, and you can see how it can generate all these colorful texture-looking images. It doesn't look very cohesive, very coherent as far as spatially. It doesn't have any recognizable class from ImageNet that you can clearly see, but you can see that it's not just a random noise. It's getting some sky-like textures, some very colorful patterns, and so on. So it's just understanding a lot about color. And then the same model architecture, Pixel RNN CNN, got extended to application for speech. So where this dilated convolutions, layer by layer, was stacked on top of each other with a masking structure, and it was applied on the problem of text-to-speech, and this resulted in the famous WaveNet that is actually now deployed on Google Assistant. And it was also applied to videos. These are videos of robot moving objects, and it looks pretty much like a real video. And that's the power of having autoregressive models decoding your future frames conditioned on the past. So the way this model worked was it processed the past frames using a convolutional LSTM and fed that as a context for a autoregressive decoder, and that's able to synthesize the future really, really well. It's hard to see any difference from whether this arm was real or not. And more recently, like just this year, on the left you can see the model that we briefly saw in the class, where tricks like conditioning on the low-bit version of the image and modeling that first, and then feeding and then learning a conditional model that translates the low-bit to the high-bit version works really well. So on the left are unconditional ImageNet samples on 128 and 256 resolutions. So even something like BigGAN hasn't really produced unconditional ImageNet samples of 256 pixels across 256 at this level of quality. So you can see there are clearly discernible classes, like you can see some dogs over here, and then actually it can even generate human-like pictures. There are some humans, and their faces are clearly visible. So much level of details. So that's very impressive. On the right, you can see a class conditional autoregressive model in a hierarchical, trained in a hierarchical fashion. Well, so we haven't taught this because this just came out like a week or week and a half ago. But you can see equality is at the level of BigGAN, or even better in terms of like the very clear dog pictures, butterflies, owls, and so on.
What's the name of that?
Second, it's called some hierarchical. We can post it on Piazza. Yeah, I can't recall the top of my head. And most of you might have seen this. This is just mind-blowing. The top black text is what is like something that humans fed in, and the autoregressive model completed it. This is the OpenAI GPT-2, basically a giant transformer with billion parameters trained on large volumes of text downloaded from the internet. And actually, you can take a moment to read it. It's really fun. So you can actually see that it takes some story about unicorns and talks about how so unicorns which were bred between humans and unicorns discovered English. So if you actually look at all these parts, so the animals were believed to be descendants of a lost race of people who lived there before the arrival of humans. Some believe that these creatures were created when a human and unicorn met each other in a time before human civilization, and it's very likely that only way of knowing if sure unicorns are indeed the descendants of a lost alien race is through DNA, but they seem to communicate in English quite well, which I believe is a sign of evolution, or at least a change in social organization, said the scientists. So all this has been generated by a language model. This is fantastic. The level of understanding, long-range reasoning, more than hundreds of words, and it's able to get proper nouns right. It's able to understand, relate things like evolutionary biology and species made. So the alien race, DNA, all these sort of things. So this is the level of progress that's been made in autoregressive models. They're amazing as far as language is concerned. So in terms of trying to put things in context of what was possible earlier compared to what's possible now. So this Radford et al. 2019, this is the one that you just saw in the previous slide. But these are the sentences that were possible several years ago by Shannon, and then by Ilya Sutskever started the first initial RNNs. They started generating something, but not as long and coherent as the one you saw earlier. So basically, all this progress has been made by moving away from n-gram models to recurrent neural networks, and then special kind of RNNs, which is LSTMs, and then the transformer architecture, and then just making the transformer bigger and bigger allowed us to see like way better sentences. So if you think about trying to summarize the salient bits of what's made these advances possible, like these are the following. Just train larger batch sizes, and that's been made possible by the availability of more compute, more hidden units, more so all your 1x1 convolutions or dense layers can just have more features. Just have more layers. For instance, GPT-2 uses like around 40 layers of transformers. Then you can figure out clever ways to condition on auxiliary variables. So if you, one of the most important pieces of the wavenet architecture was the clever way to condition the text. So you compress the text into a hidden vector, and then you condition it using the gated pixel CNN style, where you use the conditioning variable as part of your 1x1 convolution. So these are ideas that were not very trivial, but more architectural in nature, but super important in terms of enabling the progress. Very clever ways to pre-process things. So for all the GPT-2 advances are not on word or character level language modeling. They're actually run on byte level, so using byte pair encoding. Compute power, so they use TPU pods for training the GPT-2. And one very important thing is you have to wait for several days or weeks to see really good results. So the first GPT-1 version, or the predecessor to that, where OpenAI trained the sentiment neuron, were trained for months, like several weeks, 2 months or something like that. So you need to wait for a long time for these autoregressive models to converge to amazing results. And another important thing is make as few assumptions as possible. Even though prior work might have made some assumptions, you should throw away them if you think they're not worth having. So for instance, it was assumed that for images you should just be using convolutions, but self-attention was an idea first. The promise of that was primarily shown on text, but there was nothing stopping from people to try that on pixels. But then, like it might not make sense. You might think, oh, okay, all the object recognition advances have been made possible just because of the translation invariance, and therefore, for images, I should just be using convolutions. But when you question such assumptions, you can make really huge advances. Another assumption that people have broken is the fact that pixels are continuous signals. It's not the same as having categories. So a pixel of value 255 is closer to 254 compared to 1. So you should take that into account. That's nice, and that was actually used in the discretized mixture of logistics. But the first pixel RNN CNN threw away that assumption and just modeled the pixels as independent categories and a 256-way softmax. And if you actually remember in your first assignment, you implemented a 4-way softmax for the pixels, and it actually worked. So sometimes you just throw away earlier assumptions that people had, and you might see some really good results. This is highly underrated, but probably the most important of all, is architecture advances. So there are 3 fundamental ideas: mass or causal convolutions, a clever way to implement a very parallel architecture like convolutions but at the same time making sure that the future input depends only on the past, and dilated convolutions that gives you a larger receptive field than regular convolutions. This dilated convolutions idea was first shown in segmentation in computer vision, and the DeepMind people figured out that could be useful in text-to-speech and put it in the wavenet on top of the pixel RNN CNN, and that led to really very coherent text-to-speech results. And again, transformers that allow you to have a global context all over the model instead of relying on memory. So these are very fundamental advances that have made sure all these amazing results are possible. Finally, the loss function that you use really matters a lot. So one thing from supervised learning we can take is cross-entropy loss works really well. it's very well behaved, and so several successes have been made possible in unsupervised and reinforcement learning by just trying to make unsupervised learning or reinforcement learning look very much like supervised learning as far as the model architecture, the loss function, the optimizer is concerned, and that works really well. So all the pixel RNN was just cross entropy loss. Autoregressive models are cross entropy loss. So one important point to note is the wave was also pre-processed using a mu law to take it from a 65,006 categories to something of fewer categories, and then a regular cross entropy loss was applied. So you might think speech signals or acoustics are generally continuous. So how does it even make sense to use some like a discrete cross entropy loss for that? But yeah, so when you question these and try to make the whole architecture or model look very much like supervised learning, amazing advances have been made possible. So this is what's happened so far. Let's look at what can happen now. So as I said in the slide about Hinton statement, we're only scratching what's possible. So if we can train more with model parallelism, there are things like mesh TensorFlow available now, which allows you to share the model parameters across TPU cores, and that might let you to train like trillion parameter language models maybe. So if you could train trillion parameter language models on all of the internet's texts, like say Google Books or Kindle, Hacker News, Reddit, or podcasts. So you could basically try to compress all of them and store a very, very amazing language model that has really good language processing capabilities, such that you can take it on any downstream language task and it works really, really well. And then one thing that people haven't tried yet, but we're trying, is trying to use the same model but very little differences across different modalities like text and pixels. People have earlier tried using convolutions for text, and now that self-attention works really well for both pixels and text, as long as the context size is limited, you could try to train on a big text data set and a big image data set, and what is available on the internet is so big, so you can just try to compress them using self-attention blocks, but just separate the initial encoders and decoders. Maybe it learns to compress what's common across these two different domains. So on the engineering side, there are things to work on like fast sampling. So things like self-attention are still pretty slow. The models take a lot of time to train, and they're also slow for sampling. If you can write some better kernels or sparse kernels for that, and make the processing faster, sampling faster, that could be amazing. So one paper that kind of tried to do this was the wave RNN, and so the wave RNN has comparable results to a parallel wavenet, but it's basically an RNN architecture which is sparse and runs at different scales. So it's like the multi-scale pixel CNN idea. So those kinds of innovations will be more useful in the short term as far as trying to make these architectures that don't seem parallelizable or fast for sampling to be like more feasible as far as putting it on a mobile phone is concerned. Another thing that is worth trying is thinking about hybrid models where you weaken the autoregressive structure, but you still use autoregressive models, but train them on a large scale. So there are architectures like the parallel pixel CNN that reduce the dependency in terms of what each pixel depends on. You don't have to make each pixel depend on all of the past pixels in a particular ordering. You can make sure that the context size is limited, but you can still have a autoregressive model and try to make a trade-off between the level of autoregressive structure you have and the kind of sampling time it gives you with more independence assumptions. So again, like the new architecture design choices you can introduce more parameter sharing across the models, and that could give rise to better results. So self-attention is work. So what is the next self-attention those kinds of ideas are also really worth considering. Yeah.
What do you mean by leverage a lot of computational?
So if you think about it, the kind of ops that are taking place in self-attention are mostly across the matmls of the features, and that's what hogs most of the memory and time. And the actual projections from the input tensors to the query or keys are not that computation. Like they are actually happening in lower dimension because you're splitting it across different heads. So so therefore you're sharing a lot of parameters across these heads, across different samples in your batch and so on. So those and similarly, and what are these different samples in your batch? They're just different positions in your input tensor. So you're just applying the same kind of computation across the entire model. And convolutions is also one other way to do that, by just repeatedly applying a filter across it. So if you think about 1x1 convolution, you're just applying a dense matml, but the same matrix applied at different pixels. So so that's what I mean by sharing computations. So a short summary of all that would be, this is a very active topic, and probably in terms of density models, like it has the most cutting edge results, and there's a lot of scope for more engineering, more creative architecture design, trying to train it on larger models, larger data sets. And one nice thing about this is it's had success in unconditional as well as conditional audio, video, text, and images. So other models can't say the same. And also trying to trying to get down to the brass tacks of how the sampling time works. Trying to write like low-level kernels for that would be really worth it as far as making some huge progress in this field. So we'll also have to see some negatives. So one obvious negative in autoregressive models is there's no single layer of learned representation. So the people in BERT, by just taking the final layer and freezing all of the previous layers and trying to train it on downstream tasks, but it doesn't produce as good results as just fine-tuning the entire model. So unlike, say, a CPC or variational autoencoder, where you could just take the latent variables and use them, autoregressive models don't give you something like that. Another thing is the sampling time is slow for practical deployment currently, which you guys know, and it's not directly usable for downstream tasks. Like what I mean by this is not that you can't just take the model, apply it in zero shot for something, and so on. So and the final thing is that one important thing about generative models is, like, the reason why generative models appeal a lot to a lot of people is that you can do all these cool interpolations across samples. Flow models allow you to do that, and GANs allow you to do that. And that's one of the biggest reasons why GANs are so popular. People can play with it. You can just train it and put it on the internet, and people play with it. Those kinds of things are not possible for autoregressive models. You just produce a bunch of samples. So that's one negative about autoregressive models. Yeah.
Doesn't GPT-2 like zero shot beat like most of the prior state of the art? So why aren't autoregressive models directly usable for downstream tasks?
Right. So in that, they concatenate the task label before the beginning of the sequence of words. Yeah. So that's conditioning on the task. Yeah.
Oh, okay.
Yeah. I'm just talking about like naively modeling the density of the data distribution. All right. So that's about autoregressive models. Next thing we saw in the course was flow models. Flow models, we discussed various versions of it: nice, real MVP, all the way up to like Glow and Flow++. So let's look at how it went through. Started off with nice, which is basically real MVP without the scaled affine coupling, and then like it produced reasonably good MNIST digits, but the samples on CFAR and SVHN weren't that good. And then the same author made real MVP with better architectures and basically more scale and so on, and it produced much better phases, bedrooms, and the Elson data set, and some nice interpolations in ImageNet. And then does this paper GLOW, which you probably know by now, which basically took the real MVP model, removed the batch normalization, introduced ACT normalization, and a new type of flow, the 1x1 convolution flow, and made this really cool demo across celebrities and researchers. All these are really, really large phases of 56x256 resolution, and so basically, it took the success of a model that was very promising, but wasn't really demonstrated yet, and made amazing interpolations and amazing samples possible by training on like 40 GPUs for several weeks, and with lots of clever tricks like, Pieter is here. And then 5-bit. So these are 5-bit images. They tried to downscale the depth, and all these fantastic interpolations were made possible. So this is from recent work that we did, and we call it Flow++. But basically, the idea was to take real MVP and add some more ideas on top of it. And the reason I want to point this out was because apart from progress on sample quality, you can also make progress on the compression metrics, the bits per dim, and make them comparable to autoregressive models. And so, for instance, Flow++ achieves these really bits per dim on CFAR, ImageNet, and these are comparable to the pixel RNNs and CNNs, the first autoregressive models that were trained. For instance, the CFAR bits per dim is better than the pixel CNN bits per dim. It's pretty so, and similarly for ImageNet 32, it's comparable to pixel RNN. So that means that the flow models have a lot of promise in terms of trying to use modern architectures and more modern flows, and put them on a large scale, and you can produce results of comparable quality to autoregressive models, in spite of having, like the sequential sampling procedure. So, what's the future for flow models? There are lots of ideas. So you can learn the mask for coupling. You could try to keep closing the gap with autoregressive models. We're trying to use some kind of hybrid flows. You don't need constant time sampling. You could be somewhat a log of the number of pixels or something like that. This particular topic needs more research, like whether it's better to use fewer flows that are very expressive. By expressive, what I mean is just throwing a lot of layers per flow, versus just having a few layers but lots of flows. That needs more experimentation in terms of what is stable to train and so on. Usage of the multi-scale loss. It's not clear whether it helps or not. So in GLOW, every layer they take half of the variables and Gaussianize it, but instead of just Gaussianizing what you get at the end. So it's not clear how this helps in terms of producing better samples or better bits per dim. And again, the idea of using the latent variables that you get out of the flow. So you're mapping the data to the noise invertibly. So whether it's actually possible to use those noise variables and apply it to downstream tasks like classification or some other computer vision tasks is not clear. And again, how you initialize the flows matters a lot. Things like ACT norm flow or data-dependent initialization helps a lot in terms of beginning the training at the level of bits or dim that makes sense. For instance, if you're training on an 8-bit data set, you should start with approximately 8 point something as far as the training is concerned, and an ACT norm flow or data-dependent initialization helps a lot with that. So trying to probe more into those kinds of things that in stable training are very important. Another in terms of looking at it from a functional perspective, like you can think about trying to achieve GLOW level samples with fewer parameters. So the samples that you saw in the video, they use 650 million parameters. The models were really, really big. So you can't actually use them for any kind of compression or something. So trying to make sure that flows can also produce amazing samples at the level of GANs, but at the same time still have small models, because the GANs are often having very few parameters, less than 100 million parameters. And also trying to scale this up. So those samples were on 256 cross 256, so you can try to improve those to like 1 megapixel images. Trying dimensionality reduction of flows, some people are working on that. And then trying to train conditional flow models. The same kind of advances made possible with conditional autoregressive models can be made possible with conditional flow models. But it depends a lot on how you execute it, what kind of architectures you use. So the summary is there's still a long way to go before you get GAN level samples or autoregressive model level likelihood scores. And also making sure that you can train in a stable way and agree on a common set of engineering practices, like whether it makes sense to use a lot of flows or fewer flows. So it's still a very, very early field to make a lot of progress. In terms of negatives, you're going to have the noise as big as X if you don't do any kind of reductions. So the models end up becoming really big, and also this is not really a negative, but at the moment it's very brittle in terms of how you have to train it. You need to initialize it very carefully. So it's comparable to how you used to train neural networks earlier. So I mean, this is not very specific to flows. Like there are these reasons would apply even to GANs, but just want to point it out. Yeah. Cool. So after flows, we saw latent variable models, and latent variable models, like we went through the derivations of the variational lower bound, saw wake sleep and VAEs and extensions of VAEs. And these were the first results on VAEs, just on MNIST digits. Then after a while, using more modern decoders and better encoders, you can achieve like amazing interpolations of bedrooms and like whatever is possible with other autoregressive models was possible with latent variable models as well, and on ImageNet as well. And this is a model that I think we went through it in class for a while, how you can have hierarchical VAEs. It's called BIWA, and you can produce these really cool celebrity faces at the level of flow models, actually. Whatever is possible with the latest flow models on these resolutions, this particular model was able to do more or less the same. So there are some very cool applications of VAEs. I can't go through each of them, but the links are there for each of them. You can look them up. But for people who already know them, sketch RNN, world models, like learning visual concepts using the thing called beta VAE. So these are all applications where on some toy domains, you can see some really good latent variable model learning for VAEs. And so recently, there was this application of a VAE-like architecture for in rendering and robotics called the generative query networks. And this was all done in a very simple simulator. So, but the idea makes sense, where you can look at a three-dimensional world from different camera poses and learn a representation for these different poses and feed those representations to a VAE-like generative model that just decodes the output view for a different pose. And if you can do this at different locations of a 3D world, you end up mapping the entire world, and you can basically build a simulator using this two-stage pipeline. So the key thing to note here is that the latent variable models like VAEs can actually be good in terms of learning representations as well as decoding, and some promise has been shown on these simple domains. So the advantages of VAE is you get a compressed representation. By compressed, all I mean is lower dimensional. I don't really mean actual compression. It gives you an approximate log likelihood. You can interpolate using those latent variables and retrospectively see what the model has actually captured. And if you tweak some aspects of the evidence lower bound objective, like increasing the coefficient of the KL term, you might end up with more disentangled representations, as the beta VAE paper points out. And So in some sense, it's a very nice, elegant model because it behaves as a generative model, approximate density model, and it gives you latent variables that are of lower dimensions than the input, and also therefore allows you to do some kind of dimensionality reduction. So you get all of them in one model basically. Like in certain models you couldn't get one, but you got the other. Here you get everything: interpolations, generations, compression or densities, also learning some representations. So the disadvantages is that you often get blurry samples unless you really know how to train the decoders carefully with better decoders, better conditioned decoders. So if you make the regular factorized Gaussian posterior decoder assumptions, it might be too limiting. And trying to scale VAEs and show the same kind of large-scale results that flow models, autoregressive models showed, like people are still working on it, but nothing fantastic has been achieved with it yet. And all the disentanglement studies has been mainly shown on relatively very toy domains. So there's been nothing like huge representation learning success with VAEs. So in some sense, I would look at VAE as jack of all trades. It gives you everything, but if you just purely care about one thing, like if you just care about samples, you might go for a GAN. If you care about better density estimates, you might be better off using flows or autoregressive models, or representation learning might be better with all these non-generative methods. But at the same time, the fact that one model can do all of these things at once is really cool. So in terms of future, you can try to work with like more modern decoders, make the decoders little autoregressive but not too much. This is sort of on the lines of Pieter Chen's paper, variational lossy autoencoder, and then try to use more powerful posteriors, hierarchical latent variables, and then you can also experiment with discrete latent variables instead of Gaussians. So that might be able to help you prevent the posterior collapse because the KL term goes away, and try to scale VAEs with these simple tricks and produce results at the level of flow models, all the glow level celebrity results. So okay, so the next thing we're going to see is GANs. Like I guess by now it's a pretty well-established method for producing amazing samples. All of you know that, and it all started from these very simple samples till like the DC GAN results came, then the latest style GAN. So all the amazing coarse and fine interpolations of different people. You've seen all this, I guess. So these are people even made websites like this person doesn't exist using these kind of samples. So where you can actually take the style of one person at different level, different coarse and fine grain, and try to produce all these realistically looking people. And on the right you see Big GAN, and saw these interpolations in class. You can interpolate across different classes of ImageNet, and the interpolations are super smooth. So GANs are very, very cutting edge in terms of graphics and computer vision. However, so given all this progress, given this rate of improvement, it's hard to bet against them. It's hard to say they're not going to work in the long run or something like that. But there is more to be done in terms of making things work in unconditional GANs, handling more fine-grained details, like more complex scenes. So if you have a video, if you have a scene of a video or the entire video like this, where it's an actual city, a bunch of cars, bunch of people, buildings, signboards, and so on, like the current GANs might not actually work, but it's hard to bet against it. Going from the celebrity phases or ImageNet-like data sets where there's a central object in the scene to more complex scenes might be the way to go as far as pushing the capabilities. In terms of from a machine learning point of view, many successes have been made possible by introducing different ways to ensure Lipschitzness. So you can try new approaches there. You can try different conditioning tricks. A lot of progress has been made possible by trying to use the noise to dictate the batch normalization or instance normalization, and architecture design. So in big GAN, they upsample using by retaining the channels and just predicting the remaining, or downsample by just retaining them and weeding out the rest. So these kinds of ideas might help. Objective functions. So the discriminator has transformed from using a sigmoid cross entropy loss to something like a hinge loss now. So that could also change. And then like again making sure that the training can be stable and scalable. Just throwing larger models might not really help you. You'll have to make sure that things are cleverly conditioned. So if you look at the big GAN models, even though it's actually called big, the models are actually like the big GAN deep isn't that huge. The number of layers is big, but the number of parameters is still like less than 100 million, not even comparable to the kind of models being trained for flows or autoregressive models. And another idea that StyleGAN proposed was how to use the noise. So instead of feeding the noise right at the beginning, you could feed in the noise through another neural network and then use that to dictate the instance normalization at different layers and add some Gaussian perturbations at different layers. So all these are just tricks that question the first principles of why you need to use certain architectures or certain tricks. And even now you can question all of what is currently working now and try to make more advances. In terms of negatives, it's really hard to keep track of all the engineering tricks and details. And it's very, very hard. You need to spend a lot of time. You need to look at other people's code. It's not sufficient to just read the papers. And it's hard for you to know which piece is really significant. So let's say you don't have enough resources or something like that. It's hard for you to know which piece to remove. And doing all these ablations on large-scale data sets is time-consuming. So that's why people don't do it. And again, unconditional GANs are still not there yet. The sample diversity is still missing, and we also probably will keep changing to new evaluation metrics. So for instance, we use the FID metric now, but we might be using more metrics to account for generalization to a different, like a test set from the same distribution. And so I just want to point out that all these negatives aren't very specific to GANs again. Just like how a lot of engineering details matter in GANs, in the other models we've seen so far, they matter as well. So in general, generative models, it's hard to ablate because when you move to larger data sets, training time is also long. So if you want to really know if some idea worked or not, you just have to wait for several weeks. So that it's really hard to know which is the key piece that mattered. So now that we've seen all generative models, so it's important to, I mean, I'm sure like everybody has a taste, everybody has a preference for one. So which one should you use, GANs or density models? It might appear as if density models are the better ones because they might succeed in the long run or they're more principled, whereas GANs seem like a bunch of hacks. That's the general notion that people have. But it's important to keep in mind that it is not true that density models do not need the same level of engineering details as GANs. Like all kinds of tricks like conditioning, gating, layer norm, act norm. So for instance, transformers break if you don't use layer normalization. So all these things matter. These are all deep learning tricks that kept happening at some point and have become standard practices now. So it's possible that at some point the GAN architectures also converge to a fixed set of practices. And then it is not true that there's no theory for GANs either. It's just that the empirical progress is going at a rate where the theorists can't keep up with, because theory is harder. So the third thing is you can draw a parallel between having blurry samples versus having mode collapse. So we saw this in the lecture where we saw how the direction of KL between the real data distribution and the generated distribution decides what you care about. If you have the data distribution in the beginning, you care more about compression. But if you have the generated distribution in the beginning, you care more about the sample quality. So there's a parallel between having mode collapse versus having blurry samples, because it's basically the idea of placing density at points that are not on the data manifold at the cost of not missing some of the modes. And as I mentioned already, like one reason GANs are very popular. Yeah.
Is there any good way to measure mode collapse?
Yeah. So the current metrics, FID, they try to account for that. So you're trying to project to the inception feature space and trying to look at, like what the generated classes, are they covering enough classes or not, and are they covering good? Are the samples good enough that it can be classified well? So it's a heuristic. I wouldn't say it's a very principled approach to, and like not like density modeling. Yeah.
No way to optimize against it?
Some people have tried like approximately bringing in the notions of entropy, GAN, trying to make sure that there's some notion of data distribution that diverse data distribution produced, but I don't think it's an answered question. Yeah. And again, like one important thing is density models are really big. They're huge. They require large batch sizes. So you have to use distributed training. This is not doable by many people. Whereas a GAN, you can just, a single V100 GPU can help you to solve this 1 megapixel cell bay task just by training for 1 week or something. It works well with smaller models on fewer resources, and therefore more people work on it. That's the only reason that it's more popular in terms of adoption by the community. And as mentioned already, interpolations and conditional generations play an important role because generative models appeal a lot to people who are artists or any people who are generally involved in creative sciences. So GANs definitely appeal a lot more to artists, and therefore they're more popular among like people who just know about AI but don't really care about the machine learning details. But on the bright side, I just want to point out something that Jan LeCun mentioned in one of his talks in the epistemology of deep learning, where in general in scientific history, theory has often followed invention. So we discovered things like the telescope, steam engine, before actually figuring out optics or thermodynamics, feedback amplifier before actually having a good theory of electronics. And alchemists used to work on compounds before the chemistry as a science developed. This analogy is famous because in a couple of years ago in the NeurIPS conference, a person compared deep learning to alchemy, and therefore Jan LeCun, as a response to that, he came up with this history of science, saying that it's not just true between compound creation and chemistry, but several other things that we take for granted in terms of everyday engineering. The engineered output came long before the actual science was developed. So in that sense, GANs could be something like that, where right now we just keep making more and more progress on the engineering side, but maybe we figure out a more principled way to use them in the future. So this is the taxonomy of generative models. I think by now this picture should be pretty obvious to you. Like if you use likelihood, you can have implicit or explicit densities, and then implicit densities directly are optimized by GANs. We have not looked at Markov chain models in this class. And then if you use explicit densities, either it can be tractable or approximate, and if it's tractable, you can use autoregressive models like NAID, MAID, pixel RNN, or you can use change of variables formula and use flows. But the nice thing in this class we saw was that they're all the same. It's not like flows are different from autoregressive models. You can think about autoregressive model as an autoregressive flow. And then there's approximate density where you have latent variable models. And again, the Markov chain version we haven't looked at in this class. So any questions so far?
Aravind,
Yeah.
change of variable models, is that pretty pretty much the same as flow models?
Yeah. Change of variable models is so it's called nonlinear ICA. So that's actually nice, nonlinear independent components estimation, and that became real MVP, and that became GLOW, so on. So that's and general autoregressive flows, inverse autoregressive flows are generalizations of these things. So here are some guidelines. If you're training density models, if you only care about the density, if you're like doing outlier detection and don't care about sampling, let's say you're using a density model as a way to give you curiosity signals in reinforcement learning or something like that, you can just use an autoregressive model because you're not worried about sampling. If you care about sampling time but not too much, you don't really want constant time sampling, you can still use some weakly autoregressive model, or you can try to engineer on the writing really fast convolutions or self-attentions. And if you can't afford even linear, you can use log time sampling for the weak autoregressive model. One important thing to note is autoregressive models, like the actual pixel CNNs don't have to operate on discrete data. You can run the RNN or pixel CNNs on top of the continuous vectors. By discrete, all I mean is just that the final loss functions are better if they are discrete, but the actual model could operate on continuous values. So finally, flow models are good if you want to model densities of continuous value data because they're just natural. They're mapping the continuous values from one domain to Gaussians. But for discrete, we just need more progress, and we're making them, but it's still not there yet. And if you just want to try the simplest thing first, if you just want to make sure that something works at all, you just want to see some signs of life, you don't have a lot of compute, just use a variational autoencoder. Just, a carefully implemented variational autoencoder should work. I know that a lot of people were having trouble implementing it for the homework because you wrote your own KL, but if you just use the analytic KL between two Gaussians, use all these simplest posteriors and decoders, you should see some signs of life immediately. So variational autoencoder is the simplest thing to try if you want to just hack around and get results in an hour or two. And when would you use GANs? If you just want cool samples, really large images, high quality data sets, or if you want to train class conditional models, you want to apply things like image to image translation, go from segmentation mask to actual images, just keep adding more and more texture patterns, color patterns, or you only care about perceptual quality and want to control interpolations, and you don't have a lot of compute, then GAN is the best choice. So if you want to work at the intersection of machine learning and graphics, or just do more creative machine learning, creative art, I think GANs are excellent computational tools for that. So finally, let's look at self-supervised learning or representation learning. So that's what we saw at the end. Before actually going into whether it makes sense to learn generative models or not, this is a quick 3 gameplay, and let's say you were actually trying to solve this game, like train an agent to play this game, and it produces all these beams, and the pixels for these beams are not that easy to model, and there are a lot of patterns on the walls, the brick patterns on the walls, and the bullet, whatever you're being shot at, they're all having these specific pixel patterns, and so if you just care about winning the game, if you care about like mastering this environment, it's not important like what are the specific patterns on the bricks, what are the specific patterns on the walls, and so on, as long as if you can understand that these are boundaries that you can't cross, physical limitations. So so in that sense, if you just train a variational autoencoder on this, or if you train a pixel RNN or pixel CNN on this, and if you have like a lot of rooms, different color patterns on the walls, the model is just going to try to compress all of those details and think that they are very interesting, because as far as it's concerned, the raw pixels or raw observation streams, as long as they are different, as long as they they have some entropy to capture, they'll try to capture those details. But as far as intelligent behavior is concerned, all that is actually not necessary. So there are some negatives as far as trying to model all the pixels or all the raw observations is concerned. Yeah.
Okay, but for something like Minecraft has like 1 million blocks or something, and a lot of them have pretty similar textures. So for that, you would say the example of like needing to learn what the bricks look like is actually pretty important.
Yeah. So I'm not saying you should just ignore those details. I'm just saying if you go at the level of pixels, individual pixels, then anything new is interesting to you. Any changes are going to be like some kind of entropy to capture. And especially if you're given video streams of really large dimensions, it's impossible for you to actually model all over like long horizons. So modeling the pixel space is really hard for high-dimensional videos. And if you really care about developing intelligent agents that can reason over long horizons very quickly, basically faster than real time, you need to build internal world models that can run on some abstract representation. And those abstract representations must capture the useful aspects of the sensory stream and kind of trying to ignore the noise. So this is the hardest problem to solve. And I'm not saying that. Jan LeCun said that. So he just said this like I think 5 days ago. He just basically said this is the most interesting and important question in AI today, building internal world models. So what is the state of this field? I think it's like very much an open problem, and even though some promising progress has been made in like static image data sets, trying to close the gap between supervised learning and unsupervised learning, some nice transfer learning results in language like BERT, CPC, GPT, word2vec, fast text, and so on. There's been like close to nothing as far as like transfer and reinforcement learning is concerned. Pretty much nothing, and that. Originally, the motivation to work on all this was that, like, at some point, we want to take this and apply to agents that work across like hundreds of environments and figure out some simplest common explanations across them by learning some aspects of the environment that are useful to transfer. So those kinds of ideas are that's the hardest problem to solve. But even though these ideas make sense, they have actually not really worked. So the promise or the hope is that if you care about general intelligence and you want to solve problems like transfer learning or learning reusable abstractions and using those abstractions to like plan in that space, using the world model rollouts in that space, or reason using those plans, it's pretty hard, and you need to continue working on this for a while. It's not clear how far you can keep going with the current level. So let's end it with the cake. I missed the L, I guess. Yeah. So the cake summarizes pretty much everything. If you like, in terms of general intelligence, reinforcement learning comes at the end. Rewards because you don't get it's just few bits, and then supervised learning is the icing, and self-supervision, unsupervised learning, common sense, all this forms the cake, basically. So yeah, that's the summary. And let's see, maybe I can quickly run through semi-supervised learning, or
We have 25 minutes.
okay, I guess, yeah, perfect.
6:35.
Cool. So Ilya is starting at 6:45. So you have 10 minutes to eat the pizza. So let me finish semi-supervised before that. So from now on, it's just going to be more like special topics, like the course, the main topics of the course are more or less done. So I only want to cover this paper basically for semi-supervised because this paper actually takes a very critical viewpoint of whatever has happened in the field so far and try to ablate them and evaluate all of them with zero bias. So it's very nicely written. So there are 4 algorithms that I just want to quickly explain for semi-supervised. The pi model, temporal ensembling, mean teacher, and virtual adversarial training. So what is semi-supervised learning? So let's say that X is your sample, Y is your label. They're being sampled from this joint distribution. And in supervised learning, you're just trying to maximize the conditional of the label given the sample. The hope is that in semi-supervised learning, if you have a set of unlabeled samples, and if you have a set of labeled samples, is there any way in which you can leverage the unlabeled samples to improve your performance on the labeled samples? So this problem is just semi-supervised learning. You can do whatever you want in terms of how you use the unlabeled samples to improve the performance of the labeled samples. Yeah.
Is this supposed to be a log?
Oh yeah. Yeah. And yeah. Cool. So that's the goal of semi-supervised. You just have a bunch of unlabeled data, a bunch of labeled data points, and you want to improve the performance of a supervised model on the labeled data points using the unlabeled data points. And the pi model is very simple. All it does is, if you have a classifier with some stochasticities, like the noise that you add to the inputs, the kind of pre-processings that you do, like if you flip it or if you I don't know, if you add some random distortion, and also if your network has some dropout, each time you feed an input, you're going to get different outputs. So what the pi model does is it applies the regular supervised learning using this part, where it just takes the input and compares it to the true label and has a cross entropy loss. And it applies the same input stochastic encoder using two times. So you get different outputs, Zi and Zi tilde. And all it does is try to reduce the mean squared error between the two. So Zi and Zi tilde are just are the probabilities, like what you get after the softmax. And they use a mean squared error to make sure that each time you apply it to the model, you should get pretty much the same results irrespective of the stochasticities and the dropout or the kind of pre-processing that you do. And you have the weighted sum of these two losses, and this weight initially, the weight is ramped up over the course of training, so that in the beginning you're doing mostly supervised learning, and after a while you're trying to do both these objectives. So this is the pi model. Yeah, all it does is apply this mean squared error loss to penalize the model from producing different outputs for different versions of itself. And different versions of itself is very simple to augment by just using the dropout or the kind of pre-processing that you do. So you could take it to the next level by just saying that instead of relying on one model with different hyperparameters, why not just rely on the past versions of it? So you can augment, instead of getting the Zi tilde from the same model but with a different forward pass, you could just take the previous Zi tilde that you got for that particular Xi using a past version of your model. And instead of picking one particular past version, you could just have an exponential moving average of the outputs. So for every Xi, you just keep tracking the moving average of what Zis that you got with it, and you call that as Zi tilde, and you just regularize your Xi, the Zi to be close to that, in addition to doing the classification loss. And this is called temporal ensembling. So the third thing is mean teacher, where it's very similar to temporal ensembling, but the only difference is that instead of looking at the output and keeping a moving average of the outputs, just have a moving average of your parameters, and that's more efficient, so that you don't have to do it for every single sample. And this way, you can do you often do this anyway in machine learning, where you just have a EMA of your variables, so that it helps you to do better on a validation set. And therefore, you have two different models, the student model and the teacher model. And the student model runs on the data points. Teacher model takes an exponential moving average of the data parameters of the student model. And there's a consistency cost between the predictions of the student and the teacher. So, and at the end, you just throw the student model away and apply the teacher model. Yeah.
Quick question on the previous slide.
Mm-hmm.
So, or the one before that. So, how are you using like the additional data samples without any?
Yeah. So you would use the unlabeled samples only for the square difference consistency loss, and the label samples for both the losses.
Oh, I see.
Yeah. So wherever you have labels, you apply it. Wherever you don't have labels, you just apply the consistency loss. The hope is that the unlabeled points just provide some kind of structure to what kind of representations that your encoder is learning, and your cross entropy loss does the main work as far as the actual task is concerned. So next is the virtual adversarial training. I actually can't go into the details of how the sign gradient method works, but for those of you who are already familiar with adversarial examples, the way adversarial perturbations are done is you try to take the gradient of the probability of the output with respect to the input, and the noise that you add to the input is a negative times the sign of the gradient that you get from that. And if you add this kind of a noise, you can perturb the output so that for a very similar looking input, you can get a very different output. And this is basically the foundation of all the adversarial examples work. So in virtual adversarial training, what they do is they take this, they apply the perturbation to the KL between the predictions with the original sample and the predictions with the noise sample. So basically, they try to figure out a noise R to add such that this KL between your output predictions for these two is maximized. So once you can solve for this R virtual adversarial by linearizing this KL term, just like you apply it on all the data points that you have, the unlabeled data points, and this becomes your consistency cost, as opposed to how in mean teacher we're using the exponential moving average of parameters. And so let's get back to the paper. The paper compares all these techniques, and they use one single architecture for all the models, and the architecture they specifically use is the wide ResNet that uses the 3x3 convolutions in the residual block, and just uses wider filter. By wide, basically just meaning that more channels or more filters are used in the convolution. So this is typically the residual block that everybody uses, where you downsample using a 1x1 con on the channel side and apply the 3x3 on fewer channels, and then you upsample using a 1x1 con again. But for semi-supervised learning, somehow people are adopting this wide ResNet architecture. So, but that's just the detail. The main thing that you should keep in mind is the same architecture is applied for all these different techniques. And the numbers here are the error rates, the test error rates that you get by training on 4,000 labels on CFAR10. Actually, CFAR10 has 50,000 label samples, so you just use 4,000 labels. And on SVHN, you used 1,000 label points. And it turns out that the virtual adversarial training gets the best error rate compared to other models. And there is a trick called entropy minimization, which is just trying to minimize the entropy of your predictions for unlabeled samples. So you want to be confident of your outputs even for unlabeled samples. So it's like a regularizer, but it doesn't matter too much. The results are pretty comparable. Yeah.
How does virtual adversarial training using a label? So I don't see it use a label.
Oh, so there's also the supervised learning going on.
Oh, okay.
So the virtual adversarial training is for the consistency loss. So you can apply it on the unlabeled and the label points, but
It also weighted together, right? So the cross entropy loss.
Yeah,
and
yeah,
the consistent,
yeah. And for comparison, okay, so this table basically says that the authors re-implemented everything carefully with a standardized architecture, same amount of hyperparameter tuning for all of the models, and figured out that the previous authors of different techniques pointed out way higher error rates for baselines. So the pi model was earlier people used to point out that the error rate was 34 or 13%, and then like the authors of this reduced it to like 11% or 12%. So there's a wide discrepancy between what was pointed out in the original papers of each technique versus what actually ended up being re-implemented. And then you had the comparison for pre-training from ImageNet. So this is an important point to take note of, where let's say you had a much larger data set, a different data set, and you trained some representations on that, and then you transferred to CFA, but train it on a smaller data set now with 4,000 labels. You could get a lower error rate than applying semi-supervised learning directly on CFAR. So, so this basically says if you have a better representation that you got from a bigger task, you actually don't need semi-supervised learning because, yeah. Over here? Oh, the class overlap between CFA and ImageNet. Yeah. And another ablation that they did was take CFA and take fewer classes now. And so the objective of this experiment was to see if you had the unlabeled data points from a different set of classes to the labeled data points, and you're trying to do semi-supervised learning on the labeled data points, how much does semi-supervised learning actually help? And it turns out that it doesn't help a lot when there's a lot of mismatch between what classes the unlabeled data points are coming from versus what classes are actually present in the labeled data points. So if you have 6 labels and these compare the extent of overlap between or extent of mismatch between the labeled and unlabeled classes, and you can see that the test error actually goes up as the mismatch percentage grows up. So when all the classes do not belong to what is actually there in the unlabeled data points, you can see that the test error rate is much higher than just training a naive supervised learner on the smaller data set. So if you just take a smaller data set and train a naive supervised learning baseline, that beats the test error significantly compared to using semi-supervised learning when there's a complete mismatch between the label distributions. And it also turns out that this is expected, but it also turns out that as you have fewer label data points, the extent to which the semi-supervised learning methods help is not much, except for virtual adversarial training, which stays reasonably stable even as you reduce the number of label data points. But all the other techniques, the test error keeps going up as the number of label data points available to use minimized. Yeah.
So it remains stable with less data, but on like the slide 2 slides ago, it seems like there's well, like the next slide.
Oh.
Yeah, like in this slide, it seems like there's an extreme like error bar for virtual adversarial training, like much larger than the other one, right? The big yellow thing.
Yeah.
So these things like kind of.
Yeah, because it depends on which classes you leave out, which classes you actually include. So you're actually having 4. So your label data set has 6 labels. So it depends on which of the 4 you leave out and which of the 4 you have. So that decides what class overlaps and stuff. So the lessons from this paper are that if you have a standardized architecture and if you have an equal budget for tuning hyperparameters, you get very different error rates for baselines compared to what papers normally report. And if you have the unlabeled data set from a very different class distribution, then it turns out that semi-supervised learning is much worse compared to just, even if you have fewer, just a small data set, like 4,000 samples, if you have enough dropout and other regularization methods and a good architecture like wide ResNet, you can get pretty good results, much better test error results compared to using semi-supervised learning. And a key thing to note is if you use a pre-trained ImageNet, and even if there's no overlap between the ImageNet labels and the CFA labels, you can produce much better. You can produce a better lower error rate compared to using semi-supervised learning directly on CFAR. So all these conclusions are based on small data sets. So it's not clear how well they apply. Say you had a billion images which are all unlabeled, and you're trying to transfer to ImageNet. It's not clear. It's not clear if all these conclusions hold there. So. But it's interesting that you can question all these basic semi-supervised learning methods and compare them to ImageNet, or when the unlabeled data points don't share any class information with the label points. And it turns out semi-supervised learning actually isn't useful there. Cool, that's it.